Good morning, students. So let us study more about quadratic forms. Let us try to understand what do we mean by quadratic forms. So basically, quadratic forms are homogeneous polynomials of degree 2 in several variables. So for example, 2x square plus y square minus 3z square plus 5xy plus 2xz. This is a typical quadratic form. So now in statistics, they are needed when we study the probability distribution of sample variance and different sums of squares such as treatment sum of squares, error sum of squares, etc. So now let us formally define a quadratic form. So instead of x, y, z, now let us denote the variables by x1, x2 up to xn. So suppose we have n variables. Then these n variables together can be treated as a vector. So a quadratic form in the variables x1 to xn is an expression of this form q where the first term contains square terms with coefficients as alphas and the second term contains product terms where the coefficients are denoted by betas. So a typical q looks like summation alpha I xi square plus double summation beta ij xi xj where I goes from 1 to n and j goes from I plus 1 to n. So a quadratic form in n variables is typically called as n array, n-ary. So in general, unary means quadratic form in one variable would be alpha 1 x1 square. Then a binary quadratic form would be alpha 1 x1 square plus alpha 2 x2 square plus beta 1 2 x1 x2. So now a quadratic form can be expressed in terms of vectors and matrices such as x prime ax, where A is n by n symmetric matrix with components denoted by aij. So the ijth component is denoted by the letter aij. So how this aij would be? So if we consider this as the expression for the quadratic form, then aij will have diagonal elements means I equal to j will refer to diagonal elements. So the diagonal elements of this matrix capital A are equal to the coefficients of the square terms in the quadratic form, that is alpha I. And the uh, if we consider off diagonal elements, then for I less than j, it will be beta ij upon 2, and for I greater than j, it will be beta ji by 2. So thus, if A is a symmetric matrix of order n, then x prime ax is a quadratic form. So this is an alternative way to define a quadratic form. So either this way you can express a quadratic form, or you can express the quadratic form in terms of matrices and vectors like this. So a quadratic form can be expressed uniquely as x prime ax, where A is symmetric matrix and this matrix A is called as the matrix of the quadratic form. So let us now try to understand it more by going through some examples. So let us take this first example wherein we have x1 square plus x2 square minus 3x3 square plus 2x1 x2 minus 6x1 x3. So in all we have three variables. So our vector x will be having three components x1, x2 and x3. Now the coefficient of x1 square is 1. So the first diagonal element of the matrix A will be 1. The coefficient of x2 square is 1. So the second diagonal element of matrix A, that is A22, is also 1. Then the coefficient of x3 square is minus 3. So the third diagonal element of matrix A, that is A33, will be minus 3. Now the off diagonal elements are half times the uh, coefficients of the product terms. So here, so A12 will be half times coefficient of x1, x2. So it will be 2 by 2 equal to 1, which since capital A is a symmetric matrix, so A12 will be equal to A21. Similarly, the coefficient of x1, x3 is minus 6. Half of it is minus 3, so that will be equal to A13, which will be same as A31. Now, because there are no terms containing no terms of the form x1, x2, x3, so A23 will be 0, which will be same as A32, and so the matrix A will be like this, where the first row will be 1, 1, minus 3, second row is 1, 1, 0, and third row is minus 3, 0, minus 3. So similarly, x1 square plus 2x2 square minus x1 x2 can be written as a quadratic form with matrix A like this. Then x2 x3 also can be written as a quadratic form with matrix A like this, and 2x1 minus x2 plus 3x3 whole square can be written as a quadratic form with matrix A equal to this. So now let us check quickly whether you actually get what you are claiming. So let us check whether, if I take for the first example, if I take x1, x2, x3 like a three-dimensional vector with three elements, capital A like this, then do we actually get the original one? So yes, you can easily go through these calculations and can understand that actually x prime ax gives us the original quadratic form. Now here comes a very simple exercise, that what will happen if the quadratic form is equal to 0 for every vector x in Rn, n-dimensional Euclidean space. Then the matrix itself must be a null matrix. And if two quadratic forms are equal for every vector x in n-dimensional Euclidean space, then it must mean that the two matrices are equal. So show that x prime ax equal to 0 for every x implies A itself is null matrix, so A is 0, and x prime ax equal to x prime bx for every x implies that A is equal to B. So let us try to prove this. So assume that x prime ax is equal to 0 for every x. So it is true for every x in Rn. So we choose a particular value of x which is denoted by ei, and this ei has all elements 0 except the ith element, and the ith element is taking one particular value which is 1. So if we take x equal to ei, let us see what do we get. So when we take x equal to ei, then x prime ax is ei transpose A ei. Now A is a n by n matrix of this type. Then if we pre-multiply it by x prime, then we get the uh, i ith row of this matrix. So because each time I'll get ith element in each column, so I'll end up getting ith row of matrix A when I pre-multiplied by ei transpose. So I have got ai1, ai2 up to ain. Now I'll multiply this by the vector ei itself. So 0, 0, 1 will be there only in the ith position, the rest of the elements are 0. So only ith element in this matrix will appear and the rest will become 0. So I'll get this equal to aii. So thus, if I repeat this story, so thus I have got ith element to be equal to 0. Now I can allow this I to be equal to 1, 2 or any n. So if I take I equal to 1, then I'll get A11. If I take I equal to 2, then I'll get A22 and so on. Now, but we shouldn't forget that we started with the assumption that x prime ax is equal to 0 for every x. So I have gotten, this will mean that ai is equal to 0, and it will mean if I take if I vary I over 1 to n, then I'll end up getting all diagonal elements of the matrix A to be equal to 0. Now, to show that of the off diagonal elements of capital A are also 0, we particularly choose vector x as ej plus ek, where j is less than k. Now what kind of how this ej plus ek will look like? So this ej plus ek will have all elements zeros except the jth and kth element, like this. So if I take x as ej plus ek, then the quadratic form becomes x prime ax will be equal to ej plus ek transpose capital A ej plus ek. So upon simplification, let us consider the first one, the first part, that is multiplying this capital A by ej plus ek transpose. So I have jth element 1 and kth element is also 1. And now what will happen is, if I multiply this vector with the first column, then I'll get the jth and kth element of the first column, addition of jth and kth element of the first column. Similarly, if I consider its multiplication with the second column, then I'll get addition of jth and kth elements of the second column, and so on. So I'll end up getting addition of jth and kth rows of these matrices, this capital A matrix. And so I'll get aj1 plus AK1, AJ2 plus AK2 and so on up to AJN plus AKN. This will be the product of EJ plus EK transpose capital A. And now I have to multiply it by EJ plus EK. Now EJ plus EK has elements equal to 1 only at jth and kth place and rest of the elements are zeros. And so when I multiply this vector by this vector Ej plus Ek, I'll get the rest of the elements except the jth and kth element will become zeros. And the jth and kth element of this vector will get added. Now the jth element of this vector is Ajj plus Akj, and the kth element of this vector is Akk plus Ajk, and so the addition will be Ajj plus Akk plus 2 times Ajk and Akj, because A is a symmetric matrix, so I have Ajk equal to Akj. So but Ajj and Akk we have already shown that they are zeros, and so I get 2 times Ajk equal to 0, which will mean that Ajk itself is 0, and this is true for every j not equal to k, where j can vary over 1 to n and ak also can vary over 1 to n. So we end up showing that all the elements in the matrix A are zeros, which means that the matrix A itself is 0. Now let us move to the second part of the proof. Here we have to prove that x prime x equal to x prime bx for every x means A is equal to B. So let us take this on the left hand side. So this gives x prime ax minus x prime bx equal to 0 for every x, which we can simplify as x prime a minus b times x equal to 0 for every x. Now when this happens, then the matrix itself is a null matrix. So a minus b must be a null matrix, which will mean a must be equal to b. So the second part of the result is very easy to prove compared to the first part. Now let us see if we can write some matrices, some quadratic forms that we usually come across in statistics as a quadratic form. So some sum of squares, some simple things. So we start with sample mean, which is usually denoted by small x bar, which is 1 by n summation xi, if x1 to xn is represents the data. Then now the question is, if x bar denotes bin, then find the matrices of the quadratic forms n x bar square and sample variance, that is summation xi minus x bar whole square. So how do we go about this? So the first thing that we do is we express x bar, the sample mean, as a linear form in the vector x. So we take vector x as x1 to xn, and then we notice that x bar can be written as L prime x, where L prime is 1 by L prime has each element equal to 1 by n. So let us use this when we explore n x bar square. So n x bar square I can write as n x bar into x bar. So this n L prime x into L prime x. Now L prime x, I can write this as L prime x or x prime n, because it is a scalar, so 1 cross 1. So I can write it either way. So the first L prime x I am writing as x prime n, then I am multiplying it by L prime x. So I get small n is a scalar, so I am keeping it aside. So small n x transpose L L transpose x, but L L transpose will be matrix A of this type, which is basically a matrix which equals 1 by n E n n or E n, where E n denotes matrix of order n cross n with each element equal to 1. So thus we can write n x bar square as a quadratic form with matrix A equaling 1 by n E n n. E n. Similarly, summation, the sample variance, summation xi minus x bar whole square can also be written as a quadratic form like this. So what we are doing is we are expanding this. So we get summation xi minus x bar whole square. We get as summation xi square minus n times x bar square. Now n times x bar square we have already written as a quadratic form. So let us consider summation xi square. Now summation xi square is simply x prime x, which is nothing but x prime identity matrix of order n into x. So the sample variance becomes a quadratic form wherein the matrix of the quadratic form is capital B, which is equal to identity matrix minus 1 by n times the matrix of ones. So now this, let us see if this matrix is idempotent or not. So very quickly we have tried to prove here that the matrix 1 by n E n and the matrix I minus 1 by n E n are both idempotent matrices.